So welcome to 6.2, Empirical Molecular Formulas. I'm going to make two videos for this lesson. The first video will be showing you guys how to tell the difference between empirical and molecular formulas. And the second video is going to be talking about how to calculate percent composition from formulas. I'm sorry, in the first video, we'll be doing these two objectives. In the second video, we'll talk about using something called combustion analysis to determine empirical formulas of compounds, unknown compounds. And in the second video, I'll also talk about using molar mass to determine molecular formulas of unknown compounds. All right, so first, let's see if we can tell the difference between an empirical formula and a molecular formula. So your definition for an empirical formula is a formula that represents the actual number and types of atoms involved. It does not show how those atoms are connected to each other. For example, we have a molecular formula here that shows that we have 4 carbons, 10 hydrogens, and 1 oxygen in this molecule. Well, this molecule could look like this structure right here, with all the carbons being the black spheres, the hydrogens being the white spheres, and then having 1 oxygen. So we have 10 hydrogens in this molecule, we have 4 carbons in this molecule, and we have 1 oxygen. But if you look at the second structure, we still have 4 carbons, we still have 10 hydrogens, and we still have 1 oxygen, but this molecule looks very different from this one. So a molecular formula represents the actual number and types of atoms, but it doesn't show anything about how they're connected. Empirical formulas represent the lowest whole number ratio between different atoms in a molecule. So for example, if this is our molecular formula where we have 4 carbons, 10 hydrogens, and 2 oxygens, then I can report the empirical formula as 2 carbons, 5 hydrogens, and 1 oxygen. What I've done here is I've just reduced these subscript numbers to their lowest ratios. And it's important to be able to do that with molecular formulas and empirical formulas, because we're going to be learning how we're going to use something called percent composition to actually write out an empirical formula of a mystery substance. And then we'll be able to convert those empirical formulas up into molecular formulas to show the actual chemical formula of a compound. Now, the key concept to understanding how to work with empirical and molecular formulas is to make sure you understand that the subscripts in any kind of formula, the subscripts are the same thing as mole ratios between the atoms. So let's see if we can determine molecular formulas and empirical formula matches. So here we have a molecular formula of C2H6O for this one right here. So I'm looking to see if I can take these subscripts, if I can take the 2 and the 6 and the understood 1 right here, and if I can reduce those down to lower numbers by a common factor, then I know that I have an empirical formula on the other side. It looks like with a 2 and a 6 and a 1, I cannot reduce these at all. So in this particular case, the empirical formula and the molecular formula would be identical. They would be identical. Okay, now let's take a look at our next molecular formula. So we're looking at our molecular formulas first. And you can see with our second molecular formula, we have a 6 and we have a 15. Well, I could probably reduce those values down. If I take both those numbers and divide by a factor of 3, if I divide by 3, then my 6 becomes a 2 and my 15 becomes a 5. So my molecular formula can be reduced down to an empirical formula of P2O5. Okay, here we have another example of a molecular formula, and we're going to see if that molecular formula has an empirical match. So we have a understood subscript of 1 and a subscript of 2. So it looks like we do not have an ability to reduce these subscripts down to a lower value. So in this particular case, the empirical formula and the molecular formula are identical. They are the same. In my next one, I have a C12H24. So it looks like I will be able to reduce these down by a factor of, probably a factor of 12. So if I divide both of these by 12, that will give me my lowest ratio of C1H2, which is my top choice up here. And then on my last one, I have C4H10. If I can reduce my 4 and my 10 to lower values, then I'll have an empirical formula that looks different from our molecular formula. So if I divide both of these by 2, I'll end up with C2H5. Okay, so the point of this particular problem is for you to understand that empirical formulas and molecular formulas, they can be the same. Empirical and molecular formulas can be identical. And that was the case for our first example and our third example. These are two examples that show where the empirical and the molecular formula are identical. In the other cases, the molecular formulas the empirical formulas were reduced from the molecular formula, so they show the lowest possible ratios. All right, so let's move on. Determining percent composition by mass. So this is the second objective for this video lesson. You can determine the percent composition by mass of each element in a given formula. So when we determine any kind of percent, we're always taking the part of that of what we're looking at and dividing it by the whole, taking it times 100. So if we're going to determine percent composition by mass, then we need to know the total mass, and then we need to know the mass of each element. So calculate the formula mass of the given formula, and then divide that the mass of each element by the formula mass. So in this particular example, we would take the mass of this entire molecule. Just a minute here, I have these written down so I can quickly refer to them. Okay, so for this one, if I were to add up my 6 carbons, and each one weighs a total of 12, that's going to be 72 grams. And my hydrogen, I have 12 hydrogens, and each one weighs 1 off the periodic table. So that gives me a total of 12 grams. And my oxygens, I have 6 of them, and they each weigh about 16 from the periodic table. And that gives me a total of 96 grams. Now, these values right here are coming from the periodic table. These are the masses of a single mole of those substances. If I add all those up, I get 180 grams. Now, in order to find the percent composition of each element, I'm going to take the mass of each element and divide by the total. So, for example, I'm going to divide 72 by 180 grams and take that times 100. I'm going to divide 12 by 180 grams and take that times 100, and divide 96 by 180 grams and take that times 100. And I should be getting values of 40% for the carbon, 6.7% for the hydrogen, and 53% for the oxygen. And that would be my answer to this particular problem. Determine the percent composition by mass of each element in the given formula. So in this formula, 40% of the mass is coming from the carbon, 53% is coming from oxygen, and 6.7% is coming from hydrogen. So this is how you determine percent composition by mass. Now let's do a practice problem. Determine the percent composition by mass of each element in the following formula of caffeine. So this is our formula for caffeine. We have a lot to look at here. So the first thing we want to do is we want to get what is the total formula mass total formula mass of this entire molecule? Well, the entire molecule has 8 carbons, and each carbon weighs 12 grams. It has 10 hydrogens, and each hydrogen weighs 1 gram. It has 4 nitrogens, and each nitrogen weighs 14 grams. And it has 2 oxygen, and each oxygen weighs 16 grams. Now, when I multiply those values, I end up with 96 grams, 10 grams, 56 grams, and 32 grams. Adding all those up, my total is 194 grams. So then what I would do is I would divide the mass of each element by the total. Divide by 194, move my plus sign to the other side, and divide by 194 grams. And take all of those values times 100. And I end up with my mass percent of each element in caffeine. So this caffeine molecule, out of all of the elements that are in that caffeine molecule, carbon is 49% of the mass, hydrogen is 5.2% of the mass, nitrogen is 29% of the mass, and oxygen is 16% of the mass. Okay, now this is a really fun problem. It involves really massive numbers because we're going to determine the percent composition by mass of each element in the following formula, which is the largest protein molecule known to mankind, called Titan. And here's a little simulation of what that molecule might look like. It's a lot of elements. Okay, so we've got some big numbers to work with. Our carbon, we have 169,719 carbons, and each one weighs 12. The hydrogens, we have 270,466 hydrogens, and each one weighs 1 gram. For our nitrogens, we have 45,688 nitrogens, and each nitrogen weighs 14 grams. For our oxygens, we have 52,238, and each oxygen weighs 16 grams. And for our sulfurs, we have 911, and each sulfur weighs 32 grams. Okay, so these are going to be some pretty massive numbers. I'm going to have to write small so I can get all this information in here. So for our first number, I have calculated 2,036,628 grams for my carbon. I calculated 270,466 grams for my hydrogen, 639,632 grams for my nitrogen, 835,808 grams for my oxygen, and 29,152 grams for my sulfur. Now, to get the percent composition of all of these, I'm going to have to add these all up to get my total. I need my total formula mass. So if I add all those big old numbers up, I end up with 3,811,686 grams for my total. So now if I divide all these numbers, divide. If I divide all those numbers by my 3 million and take that times 100, I'm not going to rewrite my 3 million over and over and over. Then I am going to get the following percents. So Titan is 53% carbon, it's 7% hydrogen, it's 17% nitrogen, 22% oxygen, and only 0.76% sulfur. So those are our mass percentages of all of the elements found in the protein Titan. Okay, so I'm going to pause the video here, and I'll continue the video when we talk about using something percent composition to determine empirical formulas.